Question number 3.25. A ball of radius r carries a positive charge whose volume density depends on separation r from its center, and this density is changing with rho equals to rho naught 1 minus r over r. Okay, here rho naught is a constant. Okay, now the environment to equally to unity as far as the permittivity of this ball is concerned. Okay, it means the relative permittivity ER is equals to 1. Now next is, there are two parts in this question. First, we have to find out magnitude of electric field for this ball which having radius r. Okay, so in case 1 we have to find out electric field for r less than r, which means inside, and second E for r is greater than r. This is part A. In part B, we have to find out maximum intensity that corresponding to Rm. Okay, so we have to find out Rm and corresponding to that ERm, that is maximum electric field intensity. Okay, so let's see that how to approach this problem. In this problem, you can see the charge density is changing as we are moving away from its center. It means there will be variable electric field. But fortunately, it is a symmetric shape. So whenever we have a symmetric shape or charge variation, then we can apply Gauss law. Okay. So Gauss law states that total flux passing through a surface E dot ds is equals to total charge enclosed divided by epsilon naught. Okay, so we can apply the Gauss law for this radius which r is less than r. Okay, so our first case is when r is less than r. So E close integral E dot ds is equals to charge enclosed. Now let's see how we can calculate charge enclosed. If we are taking maximum radius r, then radius must change from 0 to r, right? And this is volume charge density into its volume. Okay, volume can be written as 4 pi r square into dr. Okay, because if you take a very small segment dr, so this surface area of a sphere is 4 pi r square and this width is dr upon epsilon naught. So for this side, the closed integration of this surface is surface area of a sphere. So from here we'll get ER, which is in radial direction of course, and into 4 pi r square is equals to rho naught upon epsilon naught, we can take out common, into integration 0 to r 1 minus r over r into 4 pi also can be taken out into r square dr. Right. So we need to distribute this r inside this bracket. So from here we'll get ER is equals to 4 pi and 4 pi are cancelled here, okay, on both the side. So this is rho naught upon epsilon naught into r square, and if we'll look into this integration, then we'll get r cube by 3 minus r to power 4 by 4r. Okay, so we can take out r cube from there for the ease of this expression. Then ER is rho naught into r over epsilon naught into 1 by 3 minus r upon 4r. So this is expression for electric field when R is less than R inside this volume. Okay. Now we'll assume the second case when R is greater than R. So if you draw a Gaussian surface outside of this sphere for any distance R, then here we can see that this entire sphere is covered within that Gaussian surface. So ultimately we have to calculate the total charge of this sphere for charge enclosed by the Gaussian surface, right? So again we can write that integration E dot dr is equals to total charge enclosed. Total charge enclosed is integration from 0 to r, okay, and rho naught 1 minus r over r into the surface area 4 pi r square into dr volume and divided by the epsilon naught. Or here we can integrate this term and this surface area for the outer Gaussian surface which we considered here. So ER is equals to 4 pi r square, right, and into rho naught upon epsilon naught is common into 4 pi also there, and again we'll get r cube by 3 minus r to power 4 upon 4r. Okay, so basically here we are getting r cube by 3 minus r cube by 4, right? This 4 pi would get cancelled. So from here we'll get ER for outside of the sphere when r is greater than r is equals to rho naught upon epsilon naught r square, and from here we'll get r cube by 3 minus r cube by 4, so it is r cube by 12. Okay, so this is expression for electric field outside of this sphere. Okay, now next is this is answer of part A. Now next part is what is the maximum electric field inside this sphere, because after this it is changing as r is increasing. Okay, and what is maximum value of Rm for that. So whenever we want to find out maxima of any function which is changing with certain variable, then we need to check that point by taking first differentiation of the expression. So we can put der over dr equals to 0 for E max. Okay, so we just need to differentiate this equation. Okay, so when we go for the differentiation of this, then we'll get Rm is equals to 2r by 3. Okay, by just differentiating this equation and substituting this value equals to 0. Now we'll put Rm here, then we can calculate the max value of electric field, that R equals to 2r by 3 in this expression, and from there we'll get rho naught into r over 9 epsilon naught. Okay, just put r equals to 2r by 3 in this equation, then we'll get rho naught r over 9 epsilon naught for the maximum electric field.